So in a prior video, we looked at the development of the formula for talc, which was Mg3 Si4O10 OH2. So we're going to do something a little bit different here. What if instead of silica in this fourfold coordinated site, what if we were to put in some aluminum? Now aluminum can also go into the fourfold site, but it has a 3+ charge instead of the typical 4+ charge that we have on silica. We would lose a charge, so we would have Mg3, and then we'll write Al Si3O10 OH2. Now, if this fellow over here is neutral, and it should be, then this fellow here should have a -1 charge because we've pulled out, let's just put this in square brackets. We have this structural unit here, right? The Si4O10, if we cut that in half, that is our familiar Si2O5 layers. These would have a 2- charge. If we have twice that amount, then we would have a 4- charge there. These are our tetrahedral layers. So here we still have the tetrahedral layer, but we've pulled out a positive charge. The way we would gain it back is we could add a potassium atom here. And if we did that, then we would have the mineral phlogopite. And if we exchange some of the magnesium for iron, then we could get the mineral biotite. So phlogopite is a case where we've put in some aluminum into the tetrahedrally coordinated site in place of silicon. And if we replace, let's say, 1 out of 4 of the silicon, so 1/4 of all silicon atoms are replaced with aluminum, then we would have room to put in 1 potassium per formula unit the way we've written it here. And then the pure magnesium case, again, is phlogopite. Add in some iron solid solution, and we would have biotite. Let's look at one other variation. We can have, instead of talc as our starting composition, we could start out with perophilite. So we still have the Si4O10 OH2 parts. It's the substitution of aluminum for magnesium that gives us the perophilite structure instead of talc. But we could play the same kind of game. Instead of 4 silicons, let's say that in this structural unit here, we instead have 1 out of 4 silicons replaced by aluminum. So we would have AlSi3O10 and then OH2, and then we'll have this aluminum, two aluminums here sitting in octahedral coordination. Again, we'll put in potassium to satisfy the charge that we lost in putting in an aluminum, and this fellow is muscovite. Let's write that a little bit more neatly. So this is the mineral muscovite. And as a final variation on a theme, instead of replacing just 1 out of 4 aluminums, we could replace having 1 out of 4 silicons replaced by aluminum. What if we replace 2 of 4 silicons with aluminum? Then in that case, we would have leave the Mg there. We would have Mg, Al2, Si2O10. We'll use square brackets. That indicates our tetrahedral layer, OH2. Now we've lost 2 charges. We can put in a calcium, and we can also play the same game with aluminum. So we can have CaAl2, and then Al2, Si2O10, and then OH2. And these would give us the minerals clintonite and margarite. For the case of putting in 2 aluminums here, notice that these aluminums are in 4-fold coordination and these fellows are in 6-fold coordination. That's why we write the aluminums twice. I'll have to admit that when I was a beginning student, that confused me quite a bit. Why don't we just collapse all these and just call them CaAl4 Si2O10 OH2? Doesn't that make it a little bit easier? Make it a little bit easier to memorize, that's for sure, when you're a beginning mineralogy student. But the reason for separating them here is because we're noting that the aluminums belong to two different structural sites. These aluminums here are part of the tetrahedral layer, and these two aluminums here are in the octahedral layer, coordinated to 6 oxygens instead of 4 for those aluminums there. So that's a case. This is the case for how we build up the micas. These are called the brittle micas. We're adding this 2+ charge. Calcium is an interlayer cation. Let's go back and sum up here. So for phlogopite and muscovite and biotite, potassium 1+ is the interlayer cation. So this is the interlayer cation. The way you can think of it is we have a TOT layer, and then instead of van der Waals bonds, we can have a large potassium there that bonds it to the next TOT layer. And then in the case of, let's say, clintonite, we have a calcium ion that is situated on the interlayer site. So we have a TOT layer. Here's the interlayer site, and then another TOT triplet. And we're going to put a calcium atom there, which has a 2+ charge. With a little bit greater of a charge, this triplet here is a little bit more strongly bonded to this fellow here. So the fellows with calcium as an interlayer cation are usually referred to as the brittle micas. They're a little more brittle, a little weaker than, let's say, the regular micas that have potassium or sodium on the interlayer site. That's one last chemical variation that we didn't discuss. If we take a look again at muscovite, muscovite was K-Al2 and then Al2 again, Si2O10, and then OH2. Another very important kind of substitution is putting sodium 1+ instead of potassium 1+ on that interlayer site. And if we do that, then we would have the mineral aragonite. So those are our micas.